So just to recap, we are now looking at the non-Alfvene wave solutions, or the solutions that arise from the equations that were not considered for the Alfvene waves, which are these equations in red. Okay, the equations in black were the ones which we considered earlier, and they gave the Alfvene wave solutions where the delta P, the perturbation in pressure or equivalent in density, played no role. So in this case, clearly the delta P is of central importance. So the solutions we will arrive at will involve density and pressure perturbations. So in that sense, they are somewhat similar to, or rather they have a character that is similar to the sound wave, and hence they are called magnetosonic waves. Right. So the non-Alfvene wave equations, which are just these equations in red, when written in Fourier language, become this. Okay. So you see, wherever you see an omega, you know that there used to be a d over dt. Wherever you see a k, you know that there used to be a d over dx, and so on and so forth. Okay. But mind you, because of the presence of the magnetic field, the k is not the same in all directions. Okay. The propagation vector is not the same in all directions. Hence, you have the appearance of a k sub x and a k sub z. Okay. The k sub y is already taken care of. Right. So, yeah. So now these equations can be written as a matrix times a vector equal to 0, where the vector comprises velocity Vx, Vz and magnetic field perturbations. And the important difference is that none of these involve y directed perturbations. We have already taken care of that with the Alfvene wave solutions, right? So they involve only x directed perturbations, x and z directed perturbations, of course, in velocity as well as magnetic fields. Okay, so the q is just this, and so you know, in order to have non-trivial solutions, you have to have the determinant of this matrix to be equal to 0, and so that is what's going to give us the dispersion relation. And we will be, as we will see, the dispersion relation is now this. This arises from simply, you know, determinant of a equals 0. This gives rise to this whole thing, right? So now what we've done is, instead of writing kz and kx, we write kz and k itself, where k is square root of kz square plus kx square, right? So this thing k square is simply that's what this k means. Okay, and we have made use of the sound speed as well as Alfvene speed. Both of these quantities we've defined earlier, right? So this is the dispersion relation. So this whole thing is the dispersion relation. Any dispersion relation is of the form is a relation between omega and k, and this is a relation between omega and k like the ones we saw earlier, just a little more complicated, that's all. Okay. Anyhow, let's now look at the properties of this dispersion relation. Instead of writing it in this form, instead of writing it as a function of both omega and k, you can choose to write it in this form, where u is simply the phase velocity. U over k is just the phase velocity, right? And theta, instead of writing kz and k separately, we have simply written, you know, we've simply invoked a theta, where theta is an angle between k and b. Okay, so yeah, so essentially it's kz over k is tan theta. Yeah. However you want to look at it, I mean, so theta is simply the angle between k and b, and so this is the same as this. Okay, these two equations are just the same. This just looks a little simpler. Okay, there's a way of simplifying this a little more, or rather casting this in a slightly friendlier formalism, and that's to write. And so this is a quartic equation, as you can see. There's the highest power is u raised to 4. Okay, so this is the same as this. I've simply repeated this on the next slide just for convenience. And so this equation has 4 roots clearly, simply because it's a quartic equation. Okay, it has 4 roots instead of 2 roots. A quadratic equation would have 2 roots. In this case, there are 4 roots, and these 4 roots correspond to magnetosonic waves. And as the name implies, magnetosonic, since there's a sonic in the name, it shares these waves share some properties with sound waves. And as we remarked at the very beginning of this discussion, that's no surprise, because delta p and by implication delta rho plays a central part in these waves, and so that's just like sound waves, right? So these magnetosonic waves, in that respect, they share some properties with sound waves. However, the phase speed u, which is omega over k, right, it depends upon not only the sound speed cs, right? So this is the sound speed, and this is the Alfvene speed, right? So it depends upon not only the sound speed but also the Alfvene speed and theta, which is the angle between the direction of propagation of the wave and the magnetic field. Okay, so it depends upon these 3 quantities. So another, you can cast this in a in an even simpler form by invoking a new variable u tilde, which is u over square root of cs times Va, and so this this equation essentially turns into this equation now. It's just a little bit of algebraic manipulation just to make things a little simpler. And now from this you can write, you can find out that the solutions to this quartic equation is this. All right. So there are 2 roots corresponding to u plus and u minus, roots for u squared. Okay, not just for u. The roots for u squared themselves are double valued. Okay, you can have a plus branch and a minus branch. Okay, where this quantity b is defined by this cs over Va plus Va over cs. Okay, so let me, this is a little complicated, so I'll repeat this in the next slide. Right. This is what that equation looks like. This is the dispersion equation. This is the dispersion relation for magnetosonic waves. Okay, and the other interesting thing is that for magnetosonic waves, so both kinds of magnetosonic waves, in fact, I would say, okay, both fast and slow. So the plus, if you take the plus sign here, right, this one, you get the plus branch gives you what are called fast magnetosonic waves, and the minus branch here gives you what are called slow magnetosonic waves. Okay, the dispersion relation is a little complicated. It depends upon CS, Va, not just upon the ratio but also individually upon CS and Va themselves, and on this angle theta. Okay, let us look at some limiting cases before going into the full generality. It's always good to look at limiting cases. And right, so one of the first remarks we will make is that, like Alfvene waves, the magnetosonic waves are also non-dispersive. In other words, the phase speed and the group speed do not depend upon omega. Okay, they are non-dispersive, just like sound waves, just like Alfvene waves. So in that respect, the magnetosonic waves are similar to sound waves as well as Alfvene waves, but they are anisotropic, very importantly, because why? You see the theta dependence. See, this is theta dependence, right? So there's a theta dependence here, right? So clearly the phase velocity omega over k depends upon the theta. Okay, if there was no theta dependence, they would be like sound waves, and so the direction doesn't matter. That's what having no theta dependence means. But here the direction does matter, which is to say there is a very significant anisotropy, and the anisotropy is introduced by due to the presence of the magnetic field. Okay, the magnetic field renders the medium, the properties of the medium anisotropic. Okay, so that's one important difference with the sound waves. However, Alfvene waves are also similar in this respect, in that the dispersion relation for Alfvene waves depend on k sub z, not on k itself. In other words, they depend on k cosine theta. So they also have a cosine theta dependence. Although, if you remember, here you see the Alfvene wave dispersion relation look like this, right, where the k sub z is really k cosine theta. So there is a theta dependence in the Alfvene wave dispersion relation as well. Okay, and so in that respect, magnetosonic waves are like the Alfvene waves. There is an anisotropy. The actual dependence might not be the same, but they're still anisotropic nonetheless. Right. So the other thing is the phase speed omega over k is not the same as the group speed, which is the group speed would be d omega dk. Okay. Now, I mean, as such, this equation is a little hairy. So let us look at one important limiting case. Let us look at the case where either the Alfvene velocity greatly exceeds the sound speed, or the sound speed greatly exceeds the Alfvene speed. Okay. In either case, if we look at this B, okay, if VA much greater than CS, or CS much greater than VA, what happens to B? B is much greater than 1. For instance, if CS was much larger than VA, right? So which is essentially to say that this term is much larger than 1, and this is simply the reciprocal of this term, so this would be negligible. Nonetheless, B is much larger than 1 if CS greatly exceeds VA. If the opposite is true, if VA greatly exceeds CS, then this term is much larger than 1 and this is negligible. Either way, B is much larger than 1. And where does B appear here? B appears in the denominator here, you see. B appears in the denominator. So when this is much larger than 1, this entire term becomes negligible. Okay, this entire term becomes negligible, and then what happens is the phase velocity loses its anisotropic character. So this entire term this entire chunk is not there, and you if you look only at the positive branch, in other words, if you look only at the fast magnetosonic waves, the U fast, which is the phase velocity of the fast magnetosonic wave, is simply square root of CS squared plus VA squared out here. In other words, only this one is important. This entire term becomes unimportant, right? And so you have 1 plus 1, it's 2, and that cancels with this 2 in the denominator, and you have this fairly simple looking expression. But this is valid only in these two limits. Okay, otherwise the expression is a little more complicated than that. Very important to keep in mind. We are now examining certain interesting limits. Okay, so in this limit, the fast magnetosonic speed is given by this, and the fast magnetosonic wave is no longer anisotropic. The theta dependence goes away simply because this B is much larger than 1, and this chunk becomes negligible in comparison to 1. So you might as well neglect this chunk. You might as well neglect this term which appears with the 4. All right. So in other words, as we just said, only in this case, only when the Alfvene speed greatly exceeds the sound speed, or vice versa, the sound speed greatly exceeds the Alfvene speed, the U fast is given by this, and the fast mode is isotropic, and it propagates at VA or CS, whichever is faster. What this that's also obvious, right? Suppose Cs is much larger than Va, in which case the Va squared is negligible, and so the fast magnetosonic speed is simply the sound speed. If the reverse is true, if Va is much larger than Cs, in that case the Cs is negligible, and so the velocity of propagation of the fast magnetosonic wave is simply the Alfvene wave. So that's what I mean by this statement. It propagates at Va or Cs, whichever is faster. Okay, so this is one interesting observation. For the same conditions, however, in other words, for the same conditions where B is much larger than 1, the cosine squared theta over B squared term is still negligible. But you see, you are now considering the negative sign here, so you get 1 minus 1. Right? This is still negligible, but what you need to do is that you need to, this does not, you cannot simply take 1 minus 1 to be equal to 0. What you need to do is, in this case, you need to, this entire thing needs to be expanded like 1 minus x raised to 1/2 is approximately equal to 1 minus 1/2 x for x much less than 1. It's kind of a binomial expansion. Okay. So you see, the second term is very small in comparison to 1. So that would represent x, right? And so you expand 1 minus x raised to 1/2 and you get this, and from that you arrive at this expression for the slow magnetosonic speed. Okay. So the only difference is that in this case you are taking the minus sign, whereas for the fast magnetosonic speed you were taking the plus sign. That's the only difference, but that makes all the difference in the world when it comes to, for instance, anisotropy. Okay, no matter what, the slow magnetosonic waves are still anisotropic. Okay, and what's more, U slow is slower than both Cs and Va because of this cosine theta term. Okay, so this is essentially cosine theta square times a Cs squared over Va squared over, so it would be 1 over Va squared plus 1 over Cs squared raised to minus 1. That's what this is. So that is why the U slow is slower than both Cs and Va. Okay. However, this particular expression is valid only for this condition. But the slow magnetosonic speed is slower than the slower of these two. Okay, either Va or Cs, whichever is slower, it's slower than even the slowest of these two, which is why it's called the slow magnetosonic speed, and it's anisotropic, as is evident from the appearance of this cosine squared theta, right? It's total. There is no way the anisotropy is going away. Okay, so these are two limiting cases of this dispersion relation. In general, the dispersion relation is quite complicated, but it's exactly in such cases that one seeks to examine the limiting cases and try to see what one can get out of it. Now, the other thing is, these two expressions for the fast and slow magnetosonic speed are valid for arbitrary Va and Cs. In other words, this expression and this expression. This is what I mean by these expressions. This and these two expressions for the slow and fast magnetosonic speed, of course, they are valid when Va is much larger than Cs or Cs is much larger than Va. They are valid in this case. They are also valid when these conditions are not satisfied, but if the propagation direction is nearly perpendicular to B. In other words, the cosine squared theta is much less than 1. In that case also, these two expressions are valid. The reason we're making such a big deal out of it is because these two expressions are relatively simple. They are definitely simpler than this, as you can see. Okay, and so in other words, why is that true? You see, what was the main thing? The main thing was that when VA is much larger than CS, or CS is much larger than VA, the main thing was that B is much greater than 1. Okay, so B is much greater than 1, in which case you can neglect this entire term, or rather this entire term multiplying the 4 is much smaller than 1. In the case of the fast magnetosonic speed, you could completely neglect it. In case of the slow magnetosonic speed, you take that to be a small parameter for expansion, for expanding in a binomial expansion, right? Now, if that's not the case, if B is not much larger than 1, right? In other words, if CS is not much larger than VA, or VA is not much larger than CS, if B is not much larger than 1, but on the other hand cosine squared theta is much smaller than 1, it amounts to the same thing mathematically. You see, it amounts to the same thing. Therefore, these expressions are valid for arbitrary VA and CS as well, as long as the propagation direction is nearly perpendicular to the magnetic field direction. In other words, cosine squared theta is much smaller than 1. Okay, these were two limiting cases, and since this is so we discussed the limiting cases a little bit, but now it's time to discuss the general case a little bit, and where you cannot assume that either the propagation is nearly perpendicular to B, or you cannot assume that either the sound speed or the Alfvén speed is much larger than the one is much larger than the other. So in the general case, you have to consider this full equation, and here is a kind of a diagram which helps in visualization. So what this is, so here in this case the sound speed is equal to 1/2 VA, and in this case the sound speed is equal to twice VA. Two cases. In neither case can we make the simplification that the sound speed is much smaller than or much greater than the Alfvén velocity. Okay, they are comparable. 1/2 and 2 are comparable. So how do these two cases look, right? So the B is along this direction. Okay, this is the direction of B, right? And fast mode is given by the blue line. Okay, in all cases this is the vector representing u. Okay, and so the blue line represents the fast mode, the green line represents the Alfvén mode, right, and the red line represents the slow mode. Okay, that's what I've said here. The fast mode is represented by the blue line, the green line represents the Alfvén wave, and the red line represents the slow mode. So what does this say, right? And the theta is essentially the direction between the angle of B, the direction of propagation of the wave. Okay, so you see, in this case where the sound speed is slightly lesser than the Alfvén speed, this is what the surface, if you will, for the fast mode looks like. The slow mode looks like this, right? So there's a very and you see this one looks very much like a cosine theta or cosine squared theta kind of plot, whereas here there is not much evidence for a cosine theta. There's not much evidence there is some anisotropy, but not much. Okay, and the Alfvén wave also looks fairly anisotropic. It also looks like a cosine theta. This also seems to have a cosine theta or a cosine squared theta kind of dependence, the Alfvén wave. Okay, and clearly the amplitude of the velocity for the slow mode is slower than both the amplitudes of the velocity for the fast mode as well as the Alfvén mode, and that's true here too. Okay, But the important difference between this case and this case, where the sound speed is smaller than the Alfvén's velocity and here the sound speed is larger than the Alfvén velocity, the important difference between these two cases is that the fast mode is more nearly isotropic here. Okay, here there is a little bit of flattening here, whereas here it almost looks like a perfect circle. The theta dependence is not there at all for the fast mode. Okay, and as far as anisotropy goes, in this case, the Alfvén mode and the slow mode are pretty much, they preserve the same kind of cosine squared theta dependence, except the speed difference between the Alfvén mode and the slow mode has become much smaller. Okay, the Alfvén wave is still slightly faster than the slow mode, except for propagation exactly along the magnetic field line. Okay, exactly along the magnetic field line, the Alfvén mode and the slow mode seem to have exactly the same speed, exactly the same phase speed. Okay, away from that, there is some difference. The difference is much larger in this case, but it's much smaller in this case. Okay, so we can surmise that as the sound speed becomes progressively larger than the Alfvén speed, the difference between the Alfvén mode and the slow mode goes down even more. Okay, both are quite anisotropic. Okay, but the difference in magnitudes of the magnitudes of the Alfvén speed and the slow mode speed becomes much smaller as the sound speed becomes larger in comparison with the Alfvén speed. The more this asymmetry is, in other words, the larger the sound speed in comparison to the Alfvén speed, the more isotropic the fast mode becomes. So this is the kind of, you draw these diagrams and you make these kinds of inferences. The other way of visualizing these MHD waves are these. For instance, this would be the propagation diagram for the fast mode, and this would be the propagation diagram for the slow mode. And the curves, these show the phase speed as in this diagram, and the arrows denote the direction of the group speed. So these are the phase speeds, right? Omega over k. These are omega over k, and in this case the arrows, these denote d omega dk. Okay, so these contours are still omega over k, and the arrows denote d omega over dk, and the dotted lines denote the direction of the phase speed. So you can clearly see that the d omega dk, the solid arrows, are not in general the same as the dotted lines. The group speed, this is the group speed, and the phase speed is simply omega over k, which is given by these dotted lines. The dotted lines and the solid lines do not necessarily coincide. Sometimes they do. Out here, sometimes they do. Okay, when you're exactly perpendicular, the magnetic field direction is like so. When you're exactly perpendicular to the magnetic direction, they do, but not always. Especially when you're going along the magnetic field directions, there is a considerable difference between the direction of the group speed and the phase speed. Okay, so this is another way of visualizing these things. Suffices to say that magnetosonic waves are the dispersion relation for magnetosonic waves is considerably more complicated than that of just the Alfvén waves or the sonic waves themselves. So this is where we will stop for now.